In this video, I'm going to talk about Goursat's lemma. So let's remind ourselves what the statement of this is. So we have some path, which is a triangle. So we have 3 points, and 1, 2, 3. So there's my path going around in a triangle. It's a closed, simple path, so it joins up to the end and it doesn't cross itself. And we want then to have a complex function. So we've got a function f, and we want f is holomorphic on and inside the triangle. Okay, so this means we can differentiate this complex function anywhere in the triangle or very, very close to the triangle. So what does this tell us? Well, Goursat's lemma says that in this situation, if we integrate along the path, then in fact we get 0. So how do we prove this? Well, our tactic is we're going to show that this integral is very small. In fact, it's smaller than any positive real number, so it must be 0. So let's start off by drawing a big triangle. So this is my triangle and my path, gamma, which I'll call gamma 0. Now I want to break this into some smaller triangles, so I'm going to take the point exactly halfway along each edge. So that's something like this in my picture, and then join these up. And you see I've turned my big triangle into 4 smaller triangles. Now I'm going to give these triangles names. So let's call the first one eta 1. So they're all going to go anti-clockwise. So make the second one eta 2, and the third eta 3, and the fourth eta 4. Now I want to work out the integral of my function around gamma, or gamma 0. But if you look at these internal lines here, then you can see triangle eta 1 is going to the right and triangle eta 3 is going to the left. So the contributions from these integrals are going to cancel out. And the same thing happens at these 2 points, which is really along this edge here. And in these 2 directions we're going this way and this way along this edge, so those will cancel out. So by additivity of the path integrals, we can write our integral over gamma, which is by here, as the sum of the integrals over the 4 triangles here, the integrals over these. Now, we know by Goursat's lemma that all of these should in fact be 0 because f is holomorphic. Well, at least that's where we're trying to get to, but we don't know that at this point. So let's say that we get some complex number. Say maybe the whole integral gives us a value of 5i. Okay, we get this imaginary number. And perhaps this breaks up as this sum of 4 things in the following way. Say the first 3 triangles, eta 1, eta 2, and eta 3, all give a value of I. And the fourth one gives a value of 2i. In this situation, the triangle eta 4 gives us the biggest absolute value when we integrate around it. So it's really special. We're going to consider now this triangle and forget about the other 3 triangles for a moment. So I'm going to rename this triangle gamma 1. So gamma 1 is this bottom right triangle. So we've chosen this one, remember, because it has the biggest absolute value. Now let's look at this integral we want to work out. So we know by the triangle inequality that if I take the modulus of this, then this is less than or equal to the sum of the moduluses of these things. And because we're assuming that eta 4 is the triangle that gave us the biggest absolute value, we can actually bound it even more. We can get rid of the first 3 of them, take 4 copies of the absolute value of the integral around the triangle e to the 4 and just bound our integral by this. So in our example, we said that maybe this total integral was 5i, and the absolute value of 5i, which is 5, is certainly the absolute value of the sum of those 4 parts of it, but this is also smaller than 4 times the absolute value of the biggest summand, which was 2i, so 5 is less than or equal to 8. This does work in our example. Now remember that we changed the name of e to 4 to gamma 1, so if we tidy up a bit, we get the equation that the absolute value of the integral over gamma is less than or equal to 4 times the absolute value of the integral over gamma 1 fz dz. Now I want to change gamma to gamma 0. Okay, so let's pan back out and look at our big triangle again. How big is our triangle gamma 1? In particular, what's the length of its perimeter? Well, if you look at this length here, this side, this is half the length of the big side of gamma 0. And the same is true with the other sides. This is half the length of this length here. This was how we made it. And this is half the length of this here. So, in fact, the total length of the perimeter of gamma 1 is half of the total length of the perimeter of gamma 0. So let's record that information. Let's say the length of gamma 0 is a certain number, capital L, and then the length of gamma 1 is L over 2. Okay, great. Now we do the same thing again. I'm going to zoom in on my triangle gamma 1. And I want to draw the midpoints of the 3 sides and make some more triangles by joining them up. And then I get 4 more triangles, which again I could call e to 1, e to 2, e to 3, and e to 4. And remember now that if I look at the whole of gamma 1, if I look at the integral over gamma 1, we said maybe that is equal to 2i. So the sum over these should be equal to 2i. So maybe the contributions to this integral were, we got I here, we got 5 here, we got minus 5 here, and I there. So the sum of these 4 integrals would add up to 2i. So now we want to choose the one with the biggest absolute value again. So we have a choice. We can either choose this middle triangle, or we can choose this bottom left triangle. I'm going to choose the bottom left triangle. So this is a special triangle. Let's mark it. So I'm going to call this gamma 2. Now again, I can ask about the length of gamma 2. So we already have some information about our lengths. The length of gamma 2, by the same argument, is half the length of gamma 1. So this is L over 4, or L over 2 squared. Also, because we chose gamma 2 to be one of the 4 triangles in gamma 1 which has the biggest absolute value, we can again get a bound. So we get some bound. This is less than or equal to 4 times 4 times the absolute value of the integral over gamma 2 of fz dz. We can keep on doing this over and over. So I've got my gamma 2. I split this into triangles. And I choose the one which gives me the absolute value which is biggest out of those. And then this gives me some triangle gamma 3. Maybe this is this one. Then I can break this up into triangles. And so on. Now this will give me an infinite sequence of triangles getting smaller and smaller. Now, because triangles are compact sets, we have the boundary and we have the inside, and then we know that in fact there's a point that will be contained in all of these triangles. So maybe this is my point, so we call this point W. This is a certain complex number inside our triangle. Something that will be important for us is if we draw a disk around this point, so there's a certain disk of radius r, then no matter what this radius is, for any positive real number, we can actually find a triangle completely contained in the disk, which includes the point W. So this triangle we often refer to as gamma capital N. It's gamma capital N.